We first started talking about magnetic properties, and when we did, um, we said, okay, what causes magnetic field? And the cause, of course, is a moving charge. So we have some electron, and it has a velocity, and that electron moving gives us our magnetic field. So we did it in class, kind of. You know, I broke down a ferromagnetic material, let's say an iron magnet, or I don't know, whatever. And we broke it down, we cut it in half, and we cut it in half again, and we kept cutting it half, in half, in half, until we finally got down to an atom. And so we drew the nucleus of an atom. And let's do this color. Then we had an electron cloud that goes around it. Double it up here. And that electron cloud has a current, I, and a B field then is associated on the inside as that. Well, the electron's going clockwise. The current's going counterclockwise. So you put your thumb along the current, and you curl your fingers. On the inside, if you curl your fingers along that current, you'll see that the field on the inside comes out of the page, and the field on the outside goes into the page. So that each of those atoms combine, all of those atoms combine, and they add up to one big, large magnet. We call them a permanent magnet. So, and we're talking about, let's just use iron, okay? We'll stick with iron as our ferromagnetic material. So iron gives us a permanent magnet. Okay, so we can zoom out of this, and we can assign then this atom a magnetic moment, and that's equal to its current times the area, which is very small. The current is very small, and its area, and then in the normal hat direction of that area. So that's its magnetic moment. In our case, that magnetic moment would be the dipole magnetic moment. And if we were to turn that whole thing, well, let's just draw the dipole magnetic moment as pointing toward us on the inside. Okay? Okay. All right, so without going into quantum mechanics, we can say that mu, I'm going to do a little, I'm not going to go into quantum mechanics, I'm just going to say that this mu, the one that we observe, is a combination of the orbital angular momentum of the electrons and the spin. Okay, so it gets, we're not doing quantum mechanics, so we don't have to worry about all that. But you have to keep in mind that not only are those electrons going around in a circle. Okay, they're going around in the circle. But not only that, they're spinning at the same time. So we've got the spinning of the mu s, and then we've got the overall mu L of them going around in a circle. So those two things combine, okay, and those two things combine to give us our net, okay, and this is the net right here. Okay, just a little bit of physics for you guys. Okay, so table 12.1 has mu values for common. Where are we at here? Mu values for common atoms. So there we go. Hydrogen, we've got 9.27. Helium, oh, look at helium, 0. Lithium, oxygen, there are some other famous ones that have 0. Bismuth, for example, is a notorious 0. So let's go back to our and so let's do this. Let's compare hydrogen and helium. And hydrogen 9.27 times 10 to the minus 24 amp meters squared. And helium is 0. So nice. Good. Okay, so we'll get back to helium in a second, but let's look at a box. Let's look at a box of hydrogen. So here's our box of hydrogen, and it's a gas, okay? So we're not in the solid state as of yet. We're in a gaseous state, and we've got all these atoms bouncing around, okay? And each of the atoms has a moment, right? It's dipole magnetic moment going in whatever random direction, okay? So we've got all of them going crazy in here. We don't know. It's, how hard it is to do random? It's so difficult. You think you're being random, and you're really not. Okay, so all these atoms, blah, 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 there's a bunch of them, and they're all doing that. Okay. Now, we stick a magnetic field on this thing, okay? So we're going to put a magnetic field on it. And what's going to happen is all of those poles are just like your compass on the earth, and you're walking around through the woods and you want to know what's going on and which way's north. Well, this way. I drew it upside down. North is going that way. So all of your little compass needles are going to line up. So, oh, that's not the color I want. We'll redraw our box, and all of the moments will line up like this. Okay, but they're not going to be perfectly lined up, Why is that? Because each of these guys are going to be bumping into each other, and you think you got a good thing going. You're all lined up with the field. Everything's going great, and then you smack into your friend, and they knock you off kilter, and you're all getting knocked off kilter. So each one of them really is off a little bit, right? They're all off just by a slight tad here and there. And that's due to thermal energy. Okay. We're going to be calling it UKT today. All right. So we've got this thermal energy that is, it's a potential energy. That's why I'm calling it U. It's ever present because this whole thing is at room temperature, say. Okay, so at room temperature, there's so much energy that's bouncing through there. These guys aren't going to all be perfectly lined up. They're going to be doing they're a little bit twisted compared to the actual B field, which would be straight up and down. Okay? So, good. Those guys are moving around. They're doing great. Now, here are overall mu. So this would be, if we were to sum all the mu together, this would be our total. And we would say I equals 0 to n. I'm going to get rid of that other n. That's the north n. We don't care about that n. We want to know how many of the atoms are in there. That's the n that matters. And we're doing it like that. So that would be our total. In this case, on the left, before we've added our magnetic field, so we haven't added the magnetic field yet. We're about to run it into the magnetic field, but we haven't. Look at me go. Oh, look at that. Okay. All right. I got rid of the magnetic field, finally. Okay. So there's no magnetic field. These guys are going random in their own crazy directions. Nobody knows which way's up, right? Nobody cares. It's a free-for-all. And it's all KT, right? Everybody's bouncing into each other, and KT dominates. So, fine. That means that our mu total equals 0, right? Statistically. They're all adding up together, and if it's random every direction, then it must be 0, okay? So, fine. But now we've got over here, our mu total has to be greater than 0, okay? So we've now come to a point where we have the ability to create, or we have created, a magnetic field inside just simply due to the material. So we now have a magnetic field due to the material, which is a factor of our mu. Okay? So, good. Now we've got a gas. This is a gas, and let's say we have our third step. So here's our first step, second step, third step. Our third step is we shut the magnetic field off. And what happens? Well, these guys are all bouncing around together, going this way and that way and everything, and gradually they will go back to random. And all the mu's, that total mu, will again equal 0, okay, after a certain amount of time. Okay, so random, great, gas, it's a situation where UKT easily can dominate and force this to happen. So nice, good for us. How a material responds to the B naught applied B field. How it responds to that is tells us which type of material it is. Okay, so what are the types? So we've got paramagnetic, we've got diamagnetic, and then we've got ferromagnetic. And we're going to save ferromagnetic for last because it's more easy to, it's more fun. But more than that, ferromagnetic is simply paramagnetic with a plus, okay? So it's really paramagnetic with some solid state behavior, statistical solid state behavior. Solid state. Okay. So because of the crystalline lattice that it forms, it shows an additional additional stuff. So it's paramagnetic plus, okay, with a big plus, because it's not a small effect. Okay, so yeah, all right. So let's talk about paramagnetic then, because that's the root. And we'll talk about paramagnetic, then we'll talk about diamagnetic, and then we'll get into the ferromagnetic in the end. Okay. So paramagnetic materials, let's get back to this. We've got hydrogen here, you can see 9.27. We've got lithium 9.27, oxygen, sodium. These guys, anything with a magnetic moment here, those are paramagnetic, okay? So paramagnetic substances, I'm going to call it para-M, okay? They have a net magnetic dipole. Okay, they have a net magnetic dipole moment. And once it, and by it I mean the mu, the magnetic dipole moment, it will align with the supplied or be not applied. Okay, so we are externally applying some be not to the to that. I haven't been able to record a video in forever, and of course, you know, you get a phone call, right? So, that's just the nature of the world. Entropy. Thermal random fluctuations. Everybody's going in their own way, moving around in their own way, and they bump into each other. And that's the nature of the world, and we're seeing it here today. So, magnetic dipole moment. So, the mu will align with the B not applied. Let's quickly we're going to dispel diamagnetic. Okay, we're going to run over diamagnetic real quick. So, diamagnetic. These guys have no, so mu equals 0. So, there is no mu to align with the external B naught. Okay, so fine, there's none to align with it. And instead, and what we're going to see in the next chapter is a little Lenz's law. But let's not get into that yet. We're not there yet. We want to say, okay, well, what happens? Well, what is happening? The atoms themselves fight against or oppose. So the atoms in structure, in crystalline structure, in solid state, oppose the B naught. Okay, so we'll talk more about this in a second. And instead of aligning with, so let's say our B naught points this direction, our mu points in that direction. Okay, or wants to. You know, the thermal stuff will still knock them around, but it still wants to go that way. So this is diamagnetic. And up here, the fact that they want to align, that's paramagnetic. Okay, parallel, right? And dia meaning opposed to. Okay, so good. Now, ferromagnetic, we already talked about how they are they're a little bit more interesting. And a ferromagnetic material you know what? I'm not touching them yet. We're gonna, nope, not gonna do it. Okay, let's just, yeah, there we go. All right. So let's just take a closer look at these things. Anyway, okay, we want to put them in a magnetic field, okay? And do you guys remember how to create a uniform magnetic field? Hopefully you do. And so in order to do it, you have to create a uniform magnetic field. So that will be our B naught. We want to create some B naught. Okay, how do we create that B naught? Hopefully you guys have thought about it for a little second, and we'll draw our solenoid like this. Come out here. So there's our solenoid, and I'm drawing it loosely so that we can see. Let's run our current in this way and run our current out that way, and we'll have some uniform B field going right on through. Okay. Done. Created a uniform B field. All right, so we want to do that, and of course it has to be uniform, right? Because scientists need to keep everything simple as you're trying to do your experiments and do all the whatever stuff. Okay, so we want to put a piece of material in there. It could be paramagnetic, diamagnetic, ferromagnetic, doesn't matter. We want to put something in our field and test it, right? So here we go. We're going to cut a piece of magnetic material of some type of material, and then we're going to stick it in our field. So we're going to wrap it up in our solenoid. And we'll bring that around, and we've got our current, and so we've got this thing. Okay, now which side is which? Who knows? Let's erase. Shoot. Let's erase the this side. Okay. All right. Okay, so there's our solenoid, and it's going around and whatnot. So there we go, and not too shabby. And of course, we can then turn on our B field, and our B field goes all the way through. I'm only going to draw it at the ends so that we can kind of draw some things happening in our material. What is going to happen in our material? Well, the mu can either align with or anti-align with the B field. So it'll either be aligned with or anti-aligned with the B field supplied. Okay, and we'll just draw B naught. Okay. All right, so each one of those little atoms in there will be wanting to align or anti-align their dipole moment. Okay? So far, so good. So what is the energy of that alignment and anti-alignment? Well, there's an equation back in chapter 11 that you shouldn't forget, and that is the energy, potential energy of B is equal to minus mu dot B. Okay, so the dipole magnetic moment times the dot product with the B field that is there will give us this. So our B field could either be this direction. Well, of course, our B field is that direction. But our mu could be this direction, or it could be this direction. So our delta B, our delta U B, the maximum that it could be is twice, right? If you're here and you go to here, that's 2 times. So 2 mu B, okay? So this is the maximum energy that we could get, potential energy, okay? This is our potential okay. Now, thermal energy, there's the thermal energy that, because it's at room temperature or whatever, wants to knock it all around. We're going to call that UKT. Well, for hydrogen, UKT is about, at room temp, 4.1 times 10 to the minus 21 joules. Okay? And I'm using hydrogen, so what does that mean? It means we're looking at a paramagnetic. So for a paramagnetic material. Okay, and we're going to assume that it's the metallic state of hydrogen that we're working with, and don't ask me more details than that because it may not make sense if we start asking too many questions. So we've got our UKT here. Okay, that's what we're going to be comparing with. We've got our ability to find this UB, and our UB is equal to 2 times the 9.3 times 10 to the minus 24. And then let's say we put it into a magnetic field where B naught is equal to 1.0 Tesla. So we're going to multiply that by 1.0, and that's going to give us joules. Our UB is equal to, what do I get? 1.9 times 10 to the minus 23 joules. So if we look at this and we compare that to this guy, the energy of the thermal energy of knocking them all around and bumping them out of their desire to be lined up with the B field is about 200 times, right? 2 times 2. 2 times 2 is 4. Yep. So UKT is roughly, approximately 200 times UB. So most mu per atom, so we can call them mu I, most mu I won't be aligned. Why do I always want to put two L's in a line? Because they want to follow each other? Aligned. They won't be aligned. They will want to bounce around. They won't ever want to be completely perpendicular to the B field. That's the point that they don't want to be the most, right? Because the torque at that point, since the torque is equal to mu cross B, that's the maximum torque, right? So they don't want to be there, but they will be in a lot of the other situations where the torque is minimized. And so they will either be aligned or anti-aligned mostly, but it's a crapshoot. It's a rando thing. So they don't want to be perpendicular. Okay. So the random thermal fluctuations, kick them around, and this is where we can go to that. It's not great, but it's not a terrible graph either. So we start off with random, right? We've got this material, it's got no magnetic field on the outside. We're looking at letter A here. And just random magnetic moments go in different directions. Then we've got our B field that we apply. Now, here's my problem with this picture. If you look on the right side of B, there's 3, 1, 2, 3. The third one in is basically going perpendicular, right, to the B field. And as soon as you turn the B field on, that guy won't be there. It won't. It's going to really, really line up or anti-align or whatever, but it's not going to stay there. So that's my one problem with this part B. At any rate, if you subtract out a lot of those guys, you'll still get an overall mu pointing in the direction of the B field. Okay, so the overall mu will be in the direction of the B field, and it turns out that for a paramagnetic material it is, but it's about 1/3. So 1/3 of mu end up giving mu parallel to, and this is the total mu, right? Total mu parallel to the B field supplied. So 1/3 of them. Okay, paramagnetic. It's basically weaker. It's just a weak version of ferromagnetic, but we'll see why in a second. Okay. So a nice thing to think about, or how to think about this, is this picture. The best part of this picture is D. So we go up here to the top, right to the right of A, and you can see that each of those atoms or mu's are pointing toward us, right? You do the right-hand rule and they're pointing out of the page toward us. And if you only add up what is on the outside of each of those circles, you'll get what is on the right, a net outside of the circle current. Your current will be going around the outside of the material, and so that's where D comes from. That shows us this net outside current on the very surface of the material. And it really has nothing, there's no real current to it. It's an addition of all of those currents on the inside, but if you take everything on the inside and you subtract as it's the other one's going the other direction, and you subtract and subtract and subtract and all that stuff, the only thing you're left with is that net current running around the outside. So that is a pretty nice graph. So we've got our random magnetic mu's. We've shown that they shouldn't be there, and we've shown that we have a surface current, an equivalent or effective surface current. Now it's not perfect. Okay, it's not perfect. 1/3 of the total net alignment. Okay, only 1/3. Okay, align. So, and that's paramagnetic. Okay, so let's get into it. A little susceptibility. So we've got this B field, okay? And we take that B field that we have supplied, and we're adding our material B field to it, and that's going to give us some net B field, okay? Well, let's call that B field, that net B field, let's just call it B. Okay, the book calls it B, so we're going to call it B. It's our resultant B field. All right, so if B equals that, and we also say that our material's magnetic field is equal to some chi, all right, that's chi, times the applied B field, some constant, right? It's a linear relationship. Then B is actually equal to B naught plus chi times B naught. And we can then factor it out, and we get our 1 plus chi times B naught. Okay, excuse me. So, excellent. Now, where was I? What is chi? Chi is the magnetic susceptibility Okay, so magnetic susceptibility is how susceptible is this material to the magnetic field and generating or opposing its magnetic field. Okay, so a diamagnetic material will have a certain susceptibility that is less than or maybe even less than 0 compared to a paramagnetic material. Okay, and let's get into that. Yeah, let's do that. Let's do that. Now we'll come over here and we'll look at these guys. So here's chi. We've got chi for aluminum, calcium, chromium, magnesium, bismuth, carbon, copper, lead, mercury. The ones on the left are paramagnetic and they are positive chi. And the ones on the right are diamagnetic with a negative chi. So you can tell that with our equation, I'm going to just write it right here, nice and sparkling clear. If that's negative, B is less than B naught. If it's positive, B is greater than B naught. And it's negative for diamagnetic, and it's positive for paramagnetic. So that's the state of the situation, okay? And keep in mind, ferromagnetic is a paramagnetic with a plus, a bonus, right? So any ferromagnetics are going to be in this situation. So you stick iron in a solenoid and you apply a current through the solenoid. The resulting magnetic field is going to be greater than if you had not put any iron inside at all, okay? So it's a way to boost your magnetic fields. So let's move up here a little bit, and we'll do let me see here. I got a note here about diamagnetic materials. Yeah, I'm gonna leave. Yeah, that's fine. So ferromagnetic materials. We're finally to the. Ferromagnetic. We're to the good stuff. Little history. Iron in Latin is ferrous. And fine. So anything that is ferromagnetic, it gets this Latin ferrous attached to it because iron, of course, is the oldest one that we know and love for many reasons. We know about iron. So an everyday chunk of iron. Okay, all right. Do you guys want to hear about the story of iron? All right, let's really get into it. Supernovas. Why does a star go supernova? It's because it's been using up all of its energy, smashing atoms together gravitationally in its fusion reactor. And it's gotten all this energy from the fusion reactions. It gets a whole bunch of energy till it got to a certain point, and that point is iron. Okay, it fused hydrogen and lithium and oxygen and nitrogen and I don't know, all the other ones that go in between till it gets to iron. Once it gets to iron, it no longer makes energy by fusing atoms together. Iron is as far as you get. So a star will get up to iron, and it's produced a whole lot of these guys by then. And it then does what? It can't hold itself up anymore. And it says, oh boy, I'm old and big and fat on iron, and what am I gonna do? And so then it explodes. Does the supernova thing, and it shoots iron all over the universe. And how random could the magnetic moments for iron be? How much more random could they be? They're all going shooting out into space and collecting together, and they collect in these domains, and iron for iron chunks. So we've got these domains like Switzerland, and each of them is randomly pointing in a weird, on their own way, right? They're all pointing some different direction. There could be another one here pointing that way. And we don't know. Okay, so they're all over the place. It's super random, okay? That's the most random you could be, which we'll get back to. How do you degauss something? But anyway, so we've got this random stuff going. They're pointing in all directions. So all 4 pi steradians. Okay, that means all directions. On a sphere. So you've got no net. The mu net or mu total is equal to 0. And even though you have a ferrous material, it still ends up being 0. And so you pick up a random piece of steel, and it's not going to have a magnetic, an overall magnetic field. Okay, so let's talk about the different elements. So we've got iron. We've got cobalt. We've also got nickel. And it's not nickel like that. I always wanted to put that. It's like that. And gadolinium. And finally, dysprosium. Okay. Iron, 26 protons, and it has an electron configuration 3d6 and 4s2. Cobalt, 27. And 3d7, 4s2, nickel, 28, 3d8, 4s2. Gadolinium is 64. But again, we have 4f7, 5d1, and 6s2. And then dysprosium with 66, and that's 4f10, 6s2. The reason why I'm writing these electric configurations, the electron configurations, is because it's those electron configurations that give these materials the magnetic property that they have. So it's interesting to see that they all have this extra little piece, right? And that it's that extra piece that does their justice for them. But these domains, they're not regions, they're called domains. Okay. And those domains are random, and yet they want to align with each other, and it's because of the crystalline lattice structure that they're in. So they all typically are in a BCC structure, body-centered cubic. Anyway, the two nearby want to align with each other, okay? And so they do. And by aligning with each other, they find a minimum energy. Just like on Earth, we have found our minimum energy by sitting on the surface of the planet. Gravitationally, we have our minimum energy. Okay, so the material has no BM. Okay, no BM until we supply AB naught. As soon as we do, that material, this is just a graph, okay? We're just graphing. These aren't actual, these aren't the actual vectors, okay? We're supplying B naught, and we're graphing it as this is positive B naught, this is negative B naught. We're going to graph up here, we're going to graph our B, which is the net, okay, not BM, it's the net B. So B is equal to B naught plus BM. Initially, BM and B0 are together and they do nothing. Then gradually they come up and they'll go to this point. Okay? And if we go and we flip it and we go back down to the other side, we'll end up here. So we've gone from positive B naught max to negative B naught max. Okay? But we started at 0, but now we're no longer at 0. We've already gone to this point, we've got back down to this point, and we're going to go from this point back up to this point, And if you notice, we never go back through 0 again, the origin. And this is because once you've applied B naught, then the domains will all tend to align with each other a little bit, right? So the domains started to align with each other. And if we look here, you can see it happening in C. Well, here's A, that's random. B happens, we put a magnetic field on there, and all of a sudden they start to align a little bit. And if you look in C, I'm not 100% sure. Okay, so they're looking at nickel, and they have these little arrows showing the alignments. Anyway, they've put the B field on this nickel, and gradually the little domains are going to align with each other, and gradually those domains are going to get larger and larger and larger until they incorporate each other, to the point where you'll have a completely just about thorough alignment of your magnet. Okay, so that's pretty, I think, pretty neat. So here's the graph that I drew, just from going from 0 to some point. So let's say we go up to B naught is 2 Tesla. All right, so we go up here to 2 Tesla. That's roughly 1 Tesla for the total B. I'm sorry, 10 to the minus 4 Tesla. 2 times 10 to the minus 4. That gets us up to 1 B. Okay, 1 Tesla in B. Now, let's just keep going here a little bit. This is the diagram that I drew. And this whole thing is called hysteresis. Okay, it means that the state of the system that you start in matters to the phenomena that you apply or how it will behave. So if we apply a B field to this system, depending on where it started, that's how it will behave. And it won't ever go back through 0 unless we start to degauss the material. Okay? And so that gets us back to what is degaussing. And let's go up just a little bit. So hold on, before we do hysteresis. So it's the fact that a system will respond due to the state the system is in historically. So you heard the story, don't cry wolf. You know why you don't cry wolf, because you cried wolf once, and you cried wolf twice, and then you cried wolf a third time, and you really needed help that time, but nobody's going to help you because you cried wolf so many times. They're already immune to, the system is immune to your behavior. Well, it's a similar situation, right? And depending on where you are, ferromagnetically, the application of that external B field will cause greater or less resultant B field. So, fine. So that's hysteresis. Something to know, by the way, because that's probably a testable thing. And that leads us back to finally degaussing. So what do you do to degauss something? So you could, oh boy, you could have your B here, your B naught there, and you start at 0 and you do this thing where you get to there and then you go back down over to here and then you go back up to here. Okay, fine, but you want to get back to 0. To degauss something, is to randomize that's an M, randomize the domains. So you want to put it back to non-uniform domain alignment. Okay, not easy to do, right? How do you do that? Well, you could gradually apply a B field smaller and smaller and smaller, right? You get this B field that's randomly applied smaller and smaller and smaller, but you do it in a perpendicular way. So you twist the whole thing sideways. So here's your B field now that you're applying, and you do it this way. And oh God, I don't even know how I'm going to draw this picture, but you're here, and it gradually brings you down here. Anyway, you keep twisting it, and you keep doing smaller and smaller B fields, smaller and smaller as you go, and eventually you'll have limited your net B field will shrink, will go to 0. Okay, so but you have to do it in all directions, right? You can't just do it in 2 directions. If you do it in 2 directions, that's fine. Up and down and bring it back down to 0, that's fine. But have you really randomized anything? No, but you've made the overall randomization of the domains effectively 0. So what is another way that you could do this? What is another way to degauss something? Well, you just melt it. Melt it down. Right? That's what a star would do. Throw it into a sun. That would work. If you want it back, then don't throw it into the sun. So you melt it down and then let it cool. And as it does, it will, if you let it cool in an environment where there is no external magnetic field, then your domains will be nice and small, and they will be random as, oh gosh, what's a random thing? An Irish dance. No. They will be random as, I don't know. So I don't even know. Something that's super random. My brain. Okay, so that's it, guys. Thank you. I hope you enjoyed this lecture.